Okay, I'm good.
All right. So my presentation is over YOLO v5 as well as YOLO v6 for computer vision for feature identification in transmission electron microscopes as well as related applications. So just getting into a very quick background into machine learning. Machine learning is just utilizing artificial intelligence to garner understanding from data sets that are either too large or too complex to process manually. It also has the added benefit of enabling several different forms of automation, such as autonomous driving. Some of the core applications I've just listed here: medicine, speech recognition, spam ID, optimization problems generally. And the focus of this talk is computer vision, which is in and of itself is broadly used for several different industries, some of which I have listed here, but most relevant to us is, of course, the material science. Within computer vision, there are three different kind of core subsets or variants that exist. The first, kind of the simplest, is object classification. This typically only works if you have a single object relative to the rest of your background. And it can be coupled with localization, which is the bounding box that's shown around the cat. YOLO itself is predominantly in object detection, or at least that's its strength is object detection, which is essentially that classification and localization, but it works for multiple objects, and with differentiating it from the background. And then lastly, although it's not in really the wheelhouse of YOLO's capabilities, there's also object segmentation, which is kind of just tracing the bounds of the object itself, so you can get a rough idea of how the objects in an image might be interacting with one another. So getting to CNNs, so computer vision, broadly speaking, is a convolutional neural network. And this is a system that contains three or more layers, those being your input, your hidden layer, and your extraction or output layer. And this helps identify key points of information that is relevant for the end user from the user's inputted data set. So for actual image files, you would present your image, and the computer would be able to analyze it pixel by pixel in order to do a series of different mathematical operations or convolutions, and to extract relevant output information. And so the convolution layer, as well as any sort of pooling layers and your kind of end-stage fully connected layers, if they are present within your algorithm, are all kind of put together within what is called your hidden layers. So the only real interface points for the end user, of course, would be the input and as well as the output. So again, specifically for computer vision, how this works is each neuron or each layer of your convolutions is accepting multiple different independent variables from inputs, which I have listed here as input 1, 2, and 3. Your neuron then performs computations. So this could be some sort of like matrix algebra or matrix multiplication, in order to extract key relevant features, which it passes to the next layer and eventually to your output. These computations are each done in order to produce kind of your statistical parameter dependent function, which I have listed on the right, with this y sub I equal w sub I times x sub I plus b sub I. So w is your weight and b is your bias, which can be positive or negative, as well as your weight can also be positive or negative, in order to produce a relevant output for each independent input. These outputs are then summed, and then they're passed to a activation function. From what I found, it seems like ReLU, or the rectified linear function, is the most common, and it is in fact a variation. The leaky ReLU is used in the YOLO algorithms. Then you can optionally pass it to pooling. Pooling helps improve the code's efficiency before it's eventually passed to your output or your next layer. And then this is just a schematic that I found online that kind of explains how the architecture may work. Or sorry, would work. This is just a very general interpretation where you have your actual image. It breaks it down into subsets of pixels before passing through convolutions, reactivation functions, pooling your fully connected layer, and then getting your statistical outputs, or the probability that is a specific object and where exactly it may be located. So getting into YOLO itself, YOLO is an acronym that stands for You Only Look Once. It is described, at least by the author of YOLO, as being a premier image detection convolutional neural network that works by streamlining, which means all together in one CNN, both establishing bounding boxes around the object, which identifies if the object is there and its rough position, as well as producing the image classification, which is determined from a conditional probability that there is an object in the box, and then what is the probability that it is a specific type of object, which in this image is either dogs or cats. So the benefits of YOLO when compared to some other computer vision frameworks is its speed. YOLO, as far as I could find, is much, much faster than any other computer vision kind of framework. This is ideal, of course, for real-time detection. The first build of YOLO, which I believe I have this actually on the next slide, is capable of processing images with a fairly modest computer at around 45 frames per second, and that was back in 2015. So the speed is very ideal if you're processing live feed information. It also offers high levels of accuracy and precision. Precision specifically is measured in all the papers I could find by the mean average position or precision, or just that map. The highly modular, YOLO is also very highly modular, and this is given by its very simple construction, just being one CNN, which has allowed it to be adapted and updated several times throughout the years. There's several different versions, more than just the standard 1 through 7. YOLO works well also in tandem with other CNNs, which is, I think, a critical benefit. YOLO, again, is very fast, but it's also very good at detecting the background compared to your objects, which is good starter information if it's fed into a different CNN, such as FastRCNN, which is much better with localization. The drawbacks of YOLO are as follows, again, related to localization. The largest source of error that Redmond, the original lead author of YOLO, identified was its localization problem. YOLO also offers no sort of image segmentation. It just gives you a rough bounding box. And the actual map data point with all the training data is typically reduced compared to more complex RCNN type ML frameworks. So this is a bit of word vomit, so I'm not going to say everything here, but again, this is all information from Redmond's paper. But how YOLO effectively sees is by dividing its image into an S by S grid. Within each one of these grid cells, you can determine a confidence that an object is actually within that cell and its rough position. And this is defined by the 5 key variables, which is your X and Y coordinates, which are relative to your actual grid cell, as well as the width and the height of the bounding box, which is relative to or normalized rather, to the whole image size, and the confidence score, which is shown just above with the equation 1. Conditional probabilities are then passed. So this is your same kind of confidence score, but it's a confidence score that is conditional, that you have an object in the cell, and then it identifies what type of class of object that may be. YOLO V1 possessed 24 different convolutional layers, 4 max pool type layers, as well as 2 fully connected layers, which I just caught at the end of Tommy's presentation. As Schroeder pointed out already, these 2 fully connected layers were dropped for future iterations of YOLO. And then the actual loss function is defined to the right. It looks very complicated, but essentially it's just that same intersection over union type of equation. The only difference is that they add these prefixes, these lambda values, lambda chords, and lambda no object. And that's in order to, as Redmond described the problem was, it was weighting the same loss for a small box as it was for a large box, but a large box would have relatively lower loss because it has more information contained within. So the actual lambda values, I'm forgetting off the top of my head, but I can look it up at the end of this talk, what they are in order to adjust for that condition. So specifically getting into YOLO V5, just some very quick fire information. YOLO V5 is, from what I could find, one of the most widely used computer vision algorithms, and it is the most widely used YOLO variant, at least as of right now. That might be changing soon with YOLO V7. Glenn Josher was the developer along with his company instead of Redmond. However, the development of YOLO V5 still was done in conjunction with the original developers of YOLO V1. There are 5 subvariants of YOLO from nano to extra large that are widely used for research applications. The size is indicative of how many different convolutional layers you have within the code's construct, with nano being the smallest and quickest, but also it sacrifices considerably with precision. As you can tell here, this is COCO's a data set that they use to train their performance, or train to test the performance of their computer vision algorithms. YOLO was built fully using the PyTorch framework, which is a tool for deep learning within computer science. And it also incorporated a different loss function rather than the standard just intersection over union. It is a generalized intersection over union, which is defined by the equation here, equation 3, exact details of which are a whole paper in itself from a group from Stanford. And then this is the actual network structure for YOLO V5 extra large, which certainly seems that way. Just looking at this all, I didn't have a chance to actually cell by cell break down what each component is, but the framework is much the same. You have your activation functions, which is your leaky ReLU, which is used for every single convolutional layer. I believe YOLO V1 was the exception. It had, and potentially YOLO other variants, where it had a leaky ReLU for all the layers except for the final layer, where it was just a linear function. But as far as I could tell with V5, it was just all that leaky ReLU activation function. So YOLO V6 has substantially less information on it. This is in part for 2 reasons. One, it was the first externally developed YOLO, had no involvement from the original developers. And 2, the same developers of YOLO V6 released YOLO V7 all of 1 month later, so it pretty quickly became eclipsed by the new superior version. Comparing YOLO V6 to YOLO V5, you'll find general speed and accuracy improvements. However, this is at the sacrifice of stability issues as well as modularity type problems. I didn't have a chance to look into YOLO V7, but I assume that those core issues were addressed with that build. So getting into some case studies, unfortunately, I wasn't able to find a very satisfying type biology related case study as you had asked, but I did find one case study or a couple of case studies I did still think were very interesting. So this first is done by a group that's trying to, for traffic sign recognition. This is for autonomous driving applications. So what it's doing is just a car is driving down the road with the camera, and the camera is trying to find or is searching for any sort of road sign and trying to identify what that road sign, the information that's trying to convey to the driver. So in the study, they compared both YOLO V5S or small with YOLO V5 extra large, and they compared it to SSD, which is a separate algorithm or single shot multi-box detection, in order to see what algorithm would be superior for autonomous driving applications. So we just have some general results. There are numerous figures in this paper, and I have this paper pulled up, so I can share my screen with that too if you're at all curious. But we see different sorts of identification scores, which improve as the algorithm gets trained more and more. And then we can actually see the end results for various different traffic signs appear: no U-turn through no entry, and the type of precision, which is very highly scored, as well as its recall value, which is also very highly scored. And then this is used in tandem to compute your MAP value. And as it can be clearly demonstrated, YOLO V5 dramatically outperformed the SSD algorithm, which is much of a surprise given that YOLO V5 was developed for real-time image input, which is the type of thing you would have from driving around with a camera on top of your car. This case study is a lot more relevant for this class. This is actually using a liquid cell transmission electron microscope. And what the group was trying to do was they had a solution of sodium chlorinate in water, and they were trying to find what different parameters, what different environments induce crystallization within the sample. So they're looking for sodium chloride crystals within the solution from the starting configuration, which is nothing's present, until these crystals begin to form and eventually continue to grow. So what they did was they compared the output of YOLO V5S to just a human counting the crystals as they form. And as a function of time, they identified new crystals. So what YOLO V5S identified is shown in red compared to a human eye shown in green. So as we can see, YOLO V5S still does have a very high degree of accuracy, although it takes a bit longer to identify the crystals in terms of the experimental time. In terms of real time, YOLO V5S is obviously much faster than a human going through frame by frame to try to identify crystals that are forming. They also repeated this experiment under a variety of different circumstances, some of which included crystals that formed more rapidly or more densely, which is a more complicated problem for a computer vision to actually tackle. And what they found was YOLO performed very strongly. It could actually identify crystals faster, although it had contained false positives along with that result. So this is just a general synopsis of the talk. So YOLO in general, developed by Joseph Redman as well as several of his colleagues. It is, at the time of release, and arguably still today, the premier image detection convolutional neural network. YOLO utilizes a streamlined bounding box and image identification neural network, so it's just all of it's done in a single CNN. The first version could get up to 45 frames per second. There was actually also a fast version of YOLO V1 that could do up to 155 frames per second, just by simplifying the number of convolutional layers. This is in comparison to V5. So with YOLO V5X, so the largest, most complicated YOLO V5 variant, they can still perform up to 120 frames per second. In either cases, you do have a very high degree of precision. I tried to normalize these values as best as I could, but I just take them for what they generally represented, which is that YOLO v1 on its training set had a map of around 63%. I found studies with YOLO v5 X that was tested on the same image set, and it had much improved accuracy. At the release of the first version of YOLO, it was, as I mentioned previously, by far the best image detection algorithm, especially in real time. Specifically for YOLO v5, YOLO v5 is the last of the official YOLO builds. It was released in May of 2020. It has 5 key variations from nano to extra large, which each have their own increased number of convolutional layers and memory and information size, which is given by the figure to the right. It is still, to this day, the most widely used YOLO variant. YOLO v6, by the same token, is not very widely used, and this is in large part because the YOLO v7 came out very shortly thereafter. YOLO v6 was the first externally developed code and featured the same 5 variants, that nano to extra large, and with speed and accuracy improvements over v5, but had stability issues. So here are my references, and with that concludes the main presentation component of my talk.
Okay. Right, so I have questions. So you, in the beginning, you presented a general idea about how YOLO worked, like a YOLO v1, I think. And then you moved to YOLO v5 and v6. Mm-hmm. But do you have an idea about how YOLO generally it worked? Was a concept of bounding boxes there. And then they were defining the bounding boxes with respect to the grid. Mm-hmm. And then in the later version, they introduced the concept of anchor boxes. Mm-hmm. So do you know the difference between the bounding box and the anchor box?
I did read into that, but I am blanking at the moment. So I don't think I can confidently supply an answer. But yeah, relative to the actual grid itself, it's looking at the centroid of the grid and just comparing where the object is relative to that to identify how the bounding box works. The anchor cells I'm less familiar with.
Okay, so in all the beginning versions, like especially in YOLO v1, they mm-hmm. have this concept of providing the bounding box with respect to the grid. Mm-hmm. So there were no concept of anchor boxes. So what are anchor boxes? They are predefined boxes that you create. For example, in our case, we have voids. So we know that our voids, it depends on the data that you provide. And you know that our voids are, say, 20 nanometer by 20 nanometer. So what we do is we define an anchor boxes. So what happens is when your model, it predicts your bounding boxes, it optimizes with respect to those predefined boxes. It just helps in computation because something is already predefined of that shape. And now, you have a prediction. Now the predicted bounding boxes would be, regressed. That's why it is known as YOLO is a regressor problem. Have you read about it? It's a regression that people uses this term, right?
Yes.
Again and again, they say that it's more simplified than mask-R CNN and faster-R CNN because it uses a term called regression. Mm-hmm. So this is one thing. Now, when you get these predictions, it is simply doing a very simple mathematical regression.